Good evening, everyone. We are going to start this. Okay. So this is your lecture about torque and angular momentum. And in the next lecture, we are going to discuss and we are going to talk about the MI. MI stands for moment of inertia. And in the next rolling. Okay. So this lecture and the next two lectures are going to be the important one for you for this particular chapter, because most of the questions are going to be asked on the basis of torque, and you can say moment of inertia and rolling, specifically related to torque. Or there are two formulas: torque equals to I omega and torque equals to R into F, and that is also known as moment of force. In the same way, we have L equals to R, you can say omega into, L, which is, or you can say torque, which is dL by dt, or you can say rate of change of angular momentum. And angular momentum we already done in the previous class, I think, and still we are okay. In this class, we are going to discuss in a great detail what is the angular momentum and the effect of angular momentum and the important parameters, properties of angular momentum altogether. Is this clear, everyone? Clear? So this one is going to be the important lecture for you guys in the next two. Okay, so let's start this. As we know, angular acceleration. Okay, in the previous we are done the angular acceleration, angular velocity, and relation with the linear velocity and vector product, I guess, right? So angular motion is the last class, and this class is the torque and angular momentum. Clear, everyone? So this is your recall. Simply, the rate of change of angular velocity is defined as the particle has angular velocity omega 1 at time t1 and angular velocity omega 2 at time t2. Then angular acceleration alpha is omega 2 minus omega 1 divided by t2 minus t1. Okay, this angular acceleration is also known as instantaneous angular acceleration if this time is going to be very, very small. So we done this thing. So as we know, omega, which is d theta upon dt for very short span of time, and alpha is d omega by dt for very small span of time, and that is also known as instantaneous angular acceleration. So keeping that mathematical expression or keeping that formula all together, so we can find, if I'm going to double differentiate my theta, which is a angular displacement, or you can say the displacement in rotational effect in rotational motion, at theta upon dt square. Again, this is unit is radian per second square, or you can say radian per second square. That is going to be slash in between. Okay, radian per second square, and the dimension is going to be m0 l0 t minus 2, because theta is dimensionless. If alpha is at 0, so circular or rotational motion is said to be uniform. What does it mean? It is very easy to understand. If alpha is angular acceleration is 0, so basically d omega, okay, basically d omega by dt is going to be 0. Clear? Because we know alpha, which is angular acceleration, is rate of change of angular velocity. So if it is 0, so what does it mean? It means it shows us the effect of this particular box is omega is a constant. Clear? Like in uniform acceleration, or you can say like in uniform motion, acceleration is going to be 0. So in the same, if alpha is 0, so omega is constant, and it states that if omega is constant, so it is quite simple to understand. Omega is constant means omega is not changing. Angular velocity is not changing. So angular velocity is not changing means the circular or rotational motion is said to be uniform. Is this clear, everyone? So that is very normal or easy to understand. The main thing is start from here. So very basic example you can see in your day-to-day life, the rotation, or you can say the rolling of a wheel or any particular object, and rotation of a door around the axis or around the hinges of this. So this is known as your moment of force. Moment of force or torque, simply T-O-R-Q-U-E, or moment of force is defined with this, and that is nothing but cross product of R cross F, where R is the perpendicular distance, where R is the perpendicular distance from that, where R is basically the perpendicular distance from the fixed axis. As you can see, the fixed axis here is this particular axis, and this one is my R perpendicular distance, or you can take this. Here the axis of rotation in the door system is going to be whatever the axis is attached with the wall. Okay, or in, you can say, malls or hospitals or even in parks, sometime you can see the you can say full rotatory door also. That is going to be in between an axis, and one way it is going to rotate in this way, and then again closed, and one way it is going to be open. So from one enter you're going to inside, from another it is going to be exits, and that is going to be rotated in a complete rotation or complete full circle. Okay, so if a pivoted, hinged or suspended body tends to rotate under the action of a force, it is said to be acted upon by a torque. What does it mean? If any particular object which is pivoted, hinged or suspended, okay, or it is tends to rotate. Here it is pivoted means it is hinged with this wall. The axis is fixed. Okay, so and it is going to rotate. You can see easily quite whenever we open or close the door, so that particular door is going to be rotate. Half circle it is going to be done. Okay, so that half circle is basically what it is. It is torque. So turning effect of force, you can understand very easily, or you can say more physical meaning of this torque. So torque is nothing but turning effect of force, or you can say turning effect of force. Okay, either you can write this turning effect of force, or what I preferably write rotational force, or you can say rotational effect of force, basically rotational force. So whenever we learn, whenever we understand this force in the rotation of a system or rotation of an object, rotation of a body, that particular force, or you can say rotational effect of force, any particular force which is going to rotate your body, which is going to rotate the you can say system or a object, that particular thing is known as rotation torque. Clear? So the turning effect or the turning effect of a force about the axis of rotation is called the moment of force, or torque due to the force. Clear everyone? Clear na beta? Okay. So moving ahead, these are basically the two examples. As you can see, rotation in a wheel or rotation in a door. So now the formula or mathematical expression of a torque and moment of force. So if the particle rotating in an xy plane, as you can see, that is rotating in an xy plane, this is going to be the particle P about the origin under the effect of force. Clear? So at any instant, the position vector of the particle R is going to be then torque tau equals to R cross F. This is the you are going to see and you are going to use. Okay, and torque tau equals to R F sine phi, where phi is the angle between the direction of R and F. As simple as that. As you can see, this is the force applied. This particular force have two components, that is F sine theta, F cos theta, and that is the R. Clear? So the perpendicular distance, or you can say the component of force which is perpendicular to the displacement vector. In that particular perpendicular direction, we can get the direction of a force, or sorry, direction of a torque. Is this clear, everyone? One more basic example you can learn about the torque whenever you open or close the tap of a water. So in opening or closing the tap of a water, which is completely rotatory, or even the half rotation, because right now we have a half rotatory you can say tap also, or right now we have a tap which can just give you the water after the pressing in, you can say, malls or airport. So different kind of thing, but the basic thing is whenever we rotate in this way, so it is going to close, okay, the valve, and the water is not going to coming. And whenever it is going to be anti-clock, so it is going to up a little bit, and the valve is going to you can say aside, and the water is coming from the tap. So these small things, even screw you can say in tightening and opening the screw also we applying this particular thing, which is a rotational effect of force, or basically the torque. With the screw, we can, you can say, when we rotate, so that screw is going to be inside into the plane of paper, so it is tightening. Or whenever we want to open, so we are going to anti-rotate, rotate that particular screw gauge in anti-rotate, you can say anti-clockwise direction. So the screw is going to be coming out. So these are basic simple example of a rotation in day-to-day life. Clear everyone? Okay. So now these are torque and moment of force, and we are going to talk about the special, or you can say properties. What are the important properties related to this? Like torque is an axial vector and what it is, and then torque and moment of force, the basic difference, maximum minimum point, and then you can say the torque and moment of force, like for a given force what it is. And there are 9, 10, 11, 12 properties, as you can say, or you can say the characteristics, maybe the good word, but these are the important characteristics or properties of this particular torque thing or moment of force. Clear everyone? So let's discuss one by one. So torque is an axial vector, that is its direction is always perpendicular to the plane containing vector r and f, and it is very easy. In the previous class we done this thing whenever we do this vector product. So in vector product, the three of them product are mutually perpendicular to each other in general. Okay, means f, it is going in this direction, are you applying, okay, little bit again, if f force is going in this direction and r is you applying in this direction, so this is your r, this is the force vector. So either in perpendicular up or either in perpendicular down direction, we can get the torque, as simple as that. So this is the torque. Clear everyone? So that is the saying of this. So torque is an axial vector. It is going to give you the axis. It is going to given around the axis, and it is always, you can say its direction is always perpendicular to the plane containing r and f. As you can see, this is the plane containing r and f. So it is going to be perpendicular to that, either upward direction or either downward direction. Clear? Is this clear? So with the right hand screw rule, as we already discussed this, right hand thumb rule, right hand screw rule, for a given figure, sense of rotation is anti-clockwise, so the direction of torque is perpendicular to the plane outward through the axis of rotation. From this figure they talk about on the previous page. This page they talk about. Okay, clear? Good. Now the second, the rectangular components of force, which is Fr, F cos theta, radial component of force, F phi, F sin theta, transverse component of force. So as torque tau equals to R F sin phi, or you can say R F phi. So that is position vector into transverse component of force. Basically, we are just going to get again this. They are proving this formula, torque tau equals to R cross F, and basically R F sin phi, where phi is the angle between R and this particular force direction. So thus the magnitude of a torque is given by the product of transverse component of force and its perpendicular distance from the axis of rotation. That is, torque is due to transverse component of force only. Okay, and there again we can use the vector product in the determinant form, like we do in the previous class. Is this clear everyone? So that is why it is an important equation. Okay, moving ahead, as torque tau equals to Rf sin phi and torque tau equals to R Fr sin phi. So either you can represent in this way or either you can represent in this way. It's our choice, whatever the particular thing we are going to say. So torque tau is also Fd, where d is R sin phi and this is R sin phi. So now this is the d. Okay, means the main thing I need to take here is, if this is the force, so this is d. So this is also a perpendicular thing. So taking care of this, or taking about, getting this figure here. I can draw here because there is so much space. Just a minute. Is this visible now? Clear? So from there you can see, if we want to talk the r sine phi. So this is your r and this is phi. So this displacement, this d is r sine phi. This is r sine phi. And again, it is perpendicular to the force. As you can see, this is perpendicular to the force. So the main thing is we need to take either one of the transverse component, either one of the sine phi component or perpendicular thing. Either the r sine phi or either the f sine phi. Clear everyone? So torque, force into perpendicular distance of line of action, because this is the line of action of force from the axis of rotation. This is your axis of rotation. Torque is also called the moment of force and D is called the moment or lever arm. So in questions, if you get this particular word moment or lever arm, so you get to know that is D basically, R sine phi. So directly you can multiply with the force. Or if you can get this moment of force, so basically it is torque. Clear? So even with the formula which is R sine phi, you can say and you can see that as torque tau equals to R cross F and R sine phi. So maximum RF when sine phi is maximum, that is phi equals to 90 degree and F is perpendicular to R. If mutually they are perpendicular to each other, so we can get the maximum torque, and if they are parallel, so we get the minimum torque. As simple as that. It is clear everyone? So that is quite obvious. Whenever we have a cross product, so in cross product thing, the two physical quantities are going to be given the maximum resultant thing or maximum result only and only if they are perpendicular, and they are going to give the minimum either they are parallel or anti-parallel. Parallel means they have the angle 0 degree or 180 degree. So in both the cases we can get the minimum. Clear? The next thing, for a given force and angle, magnitude of torque depends on R. The more is the value of R, the more will be the torque and easier to rotate the body. That you can understand from the example of a door. Why we have the door handles exactly in between or far away from the axis? Just because, as we know, this formula torque tau equals to R cross F, or tau equals to R cross F, and you can say R F sine theta, or transverse component of force sine theta, right? So the more R we apply, okay, the more R we apply, the lesser force we need to apply to maintain the same amount of torque. As you can learn from here, you can get the idea. If the torque is 20, okay, 20 Newton meter, and if the R is 10, so you we need to apply only 2 Newton of force. But if I can do the reverse, means the R is going to be shrunken down approx 4. So we need to apply 5 Newton of force at least, because 5 into 4 is 20. Is this clear? So that is why the handle of a door is exactly in between. So it can make a perpendicular angle completely. So if the angle is 90 degree, so only the torque, the magnitude is remain, right? Or you can say perpendicular distance R into F, and we make R as much as possible large to you can say easily open or close the door. And that is why it is not attached exactly near to the hinge, near to the axis of a rotation of a door. Clear na? Okay. So that is all about this thing. So the more will be the torque, or you can say, and the easier to rotate the body. Examples, what we are talking right now, the first one exactly we talk, handles are provided near the free edge. Free edge means which is going to rotate of the plank of the door. The handle of a screwdriver is taken thick. Okay. In villages, handle of you can say floor mill is placed near the circumference. Means Floor means what? If anyone is belongs from the, you can say, so-called villages, which is proper villages. So in proper villages, we you can say convert the wheat into the floor with the help of a, you can say, rotatory stone. So in that particular rotatory stone, or you can say that is look like a charkha, Gandhi ji ka charkha kind of thing. So that charkha is, or you can say that floor converting component or instrument or machine, which is basically from stone, heavy stones. So the rotatory handle is very, you can say, far away from the center, or you can say exactly near to the circumference. Okay, and somewhere it look like in this way. Okay, just a minute. This is your base of this particular, and kind of you can understand this. These are the two stones, and at this point far away we have a handle. Okay, so if you rotate this handle, because obviously it is far away from the center, right? So to make the torque more, this handle is going to be you can say stick to this instead of at the center. So we need to apply lesser amount of force so it can easily rotate, and in between we can put the grains, pulses, rice sometimes, and wheat mostly to get the flour. Got it? And maybe you hear the story from your grandmother, you can say nanny, or I mean the mother side, grandmother, and the father side. So we do a lot of hard work just to fulfill the stomach of your father and mother, right? So they usually, I mean, convert the wheat or any particular another kind of, you can say pulse or rices and so and so. I mean, different kinds of flours we have, and that is the forefathers, and at least the fathers of ours are very healthy because they do a lot of hard work in day-to-day life. And, okay, so these are the basic example of this. The handle of a hand pump, that I think everyone know, is kept along, and again the hand pump long is going to be kept long. Why so? To make it easily the torque, and you can feel it if you hold that particular you can say handle of a hand pump very near to the, you can say, rotatory thing. So that is going to be, you need to apply a lot of amount of force. So again the torque and this R increasing thing is going to be work there. The arm of a wrench used for opening the tap is you can say kept long. So in most of the, in not most, in all of the cases we given you the example of making R greater to make torque greater, and you need to apply a lower amount of force. As simple as that. Clear everyone? Clear na this thing? Good. These are the units of this torque: Newton meter, MKS unit, and Dyne centimeter, CGS. Dimension is ML2 T minus 2, because we know the force have a unit mass into acceleration ML T minus 2, and when I multiply this R, which is L only, okay, because R cross F, so in this way we can get torque. Okay, that is ML2 T minus 2, and that is the same unit with the work done, if I'm not wrong. Work done have force into displacement ML2 T minus 2, and the same energy unit it is. Clear? Okay. If a body is acted upon more than one forces, the total torque is the vector sum of each torque. That is very easy. Like in the previous class, in the first class we done the moment of inertia, you can say M1 R1, M2 R2, and you can say velocity of center of mass M1 V1, M2 V2, M3 V3, and the total force due to this, you can say the total external force on any particular rigid body is going to be F1 plus F2 plus F3 plus F4, and so and so. In the same way, the total torque tau is going to be T1, T2, T3, T4, and Tn. Okay, and you can rewrite this thing. Torque, total torque is going to be I equals to N torque of I, and that is this. Clear everyone? So a body is said to be in rotational equilibrium if the resultant torque on acting on the or it is 0. So that is very important. Maximum number of times you hear this terminology and you don't know what to do or what particular thing it is given in questions. So whenever any particular question you can get, find a point where the rotational equilibrium is there. Okay, and find a point of rotational equilibrium in that particular system, for that particular body. So that is it. So the meaning of this thing, you need to find that particular point where the net torque of the the net torque on that particular body is going to be 0. Net torque is 0 means the sum of all the torques on this particular thing is going to be 0. Clear? In case of beam balance, that is the beam balance, or seesaw. Seesaw, you everyone know, if I am not wrong, right? Seesaw, everyone play in the ground and everywhere. You can see the seesaw. So the seesaw system will be rotational equilibrium if tau 1 plus tau 2 going to be 0. What does it mean? As you can see, that is your L1, okay, and that is your L2. So F1 L1 force is going to be obviously downward for this also, and if it is going downward, so that is going to be upward, and if it is going downward, so that is going to be upward. So in both of the cases, if the force is upward or the direction is upward, so the torque is going to be completely dependent on this length or force. Why? So because easily you can see the angle here is 90 degree, and we know torque is you can say L F sine theta. Here theta is 90 degree. So directly we can write torque tau equals to force into L or L into F, whatever you wanted to write. Okay. So then torque tau 1, torque tau 2. Now see, as you can see, why it is going to be F2, because obviously it is quite obvious if the force on this particular side is going to be downward and we see this thing in a seesaw, so that is going to be you can say mandatorily or necessarily upward. Clear? So that is why making this direction opposite, F1 L1 is going to be minus of F2 L2 0, and therefore F1 L1 equals to F2 L2. However, if tau 1 greater than tau 2, so the LHS move downward. Simple thing. If tau 1 is greater than tau 2. Okay, so that is the case. Or if it is going to be more, or you can say it is going to be down or it is going to be up. So in this particular case, tau 2 greater than tau 1. Yeah. Okay. And will move downward if tau 1 going to be lesser than the tau 2. RHS move up downward, and the system will not be in rotational equilibrium. So it is not going to be rotational equilibrium unless the torque on the both of the side is going to be equal. As simple as that. And this condition is going to be fulfilled. F1 L1 equals to F2 L2. So that is also the important aspect. Is this clear? Good. So now on rotating or tilting, as you can see, on tilting a body will restore its initial position due to the torque of weight about the point O till the line of action of weight passes through its base. On tilting, a body will topple due to the torque or weight about O if the line of action of weight does not passes through the base. What does it mean? Whenever we tilt, so due to this tilt, the body is going to completely rotate itself due to the base, due to the weight of that particular body, or due to the this particular torque around this particular axis. Clear? Means we see that now whenever we move, whenever we transport any particular heavy object from one position to another position. So majorly we are going to you can say hold by the 2 people or 3 people sometimes. So we say in generally don't you can say high up that particular position, because it is going to be topple up. It is going to be fell down, and if it is going to be fell down once, or you can say if you not take care that particular heavy object in a proper manner with some angle, with some you can say final point. So once it is cross the limit of this particular topple, it is going to be, you cannot hold that. And we use this scenario to move heavy objects. For example, you can see somewhere you can say garages, the heavy wheels of a, you can say, truck or you can say tractor, they move this particular truck and tractor wheels in this toppling manner because they cannot slide them. They are so heavy. So what they do, from one side they you can say lift up a little bit and then throw it out. So it is going to be automatically topple up due to its weight and due to the torque. And then again from that this side they are going to lift up and topple up. I mean this topple up. Okay. So due to the weight, due to the torque, it is going to be moved in this toppling manner from one point to another point. I'm talking about right now the heavy wheels of, you can say, truck, bus or tractors, even from even for few big cars also. Clear? Sorry. Okay, so this is related to the, I mean this, the torque is cause of rotatory motion, and in rotational motion it plays the same role as a force plays in translatory motion, that is torque is a rotational analog of force. This all evident from the following correspondence between rotatory and translatory motion. So this is the rotational motion, or you can say rotatory motion. There is a translation motion, and exactly we have the same thing as I already given to you this thing. Torque tau equals to I alpha. Okay, and basically I is going to be mr square for any particular object. How so? Because torque tau is r and f, and if I divide this you can say with the alpha, so I can get I, which is mr square. I is basically moment of inertia. Moment of inertia, which is play the same role as a mass in translation thing. Okay, so as we know, force equals to mass into acceleration. In the same sense, we have this torque tau equals to I alpha. As we know, work done equals to F into ds. In the same sense, we have this work done equals to torque tau into d theta, because theta there is the displacement. In the same sense, we have power, which you can say torque into velocity, and in the same sense, like we already proved that power equals to force into velocity. In the same sense, we have a power in a rotational effect or rotation, which is torque into omega. In the same sense, torque is dl by dt. L is where? L is angular momentum, and r cross p. Clear? So if I'm going to differentiate this way, so you can directly see that dl by dt, r is going to remain same, right? So that is going to r, r, okay, dp by dt. Why shouldn't I do this? Even we can, if we want, it is going to give me 0, because r here in general is fixed or constant. Okay, so if it is constant, so this on the second term dr by dt is 0. So initially we can see that dl by dt, which is r cross f, is nothing but torque. Clear, everyone? Clear na? And as we know, v equals to omega r. In the same sense, we have alpha equals to a into r, right? Linear acceleration equals to alpha into r. So beta, alpha here, as you can see, alpha here is going to be acceleration by r. Clear? Why I am doing this? Just a minute, give me some time. As we know, torque tau equals to r cross f. Suppose they are perpendicular to each other, r f only. If r perpendicular to f. Clear na? So torque tau equals to r ma. R ma. Clear? now I put linear acceleration into the form of alpha. So I can do that r is okay. I can do that m r square alpha. Is this clear? So this m r square take place like a moment of inertia, like a mass in this scenario. And then we can write torque tau equals to I alpha, where I is basically moment of inertia mi, not Mumbai Indians, and that is mr square. Okay, that is mr square for any general body, and you can say, as I already given to you, and half mr square for circular ring, and so on. So that is how we can write these things. Torque tau equals to I alpha, force into mass integration. Is this clear, everyone? I mean, with this small derivation, I can give you the detailed relation between these two. Clear na? So this page or this point or this table is very, very important. If you have any question query till now, so you can ask, because the next slide is going to be your question slide. Do you have any question query, anyone? Because the next two things you need to do as a, and deliberately I tell you this I thing because you are going to use this thing in next questions. Is this clear, everyone? Okay, do this then. Magnitude of torque. You need to just use the cross product. Force is given and x at a point, r is given, because it is meter, as you can read it. Okay, as you can directly read it, it is meter. So obviously it is r, and it is Newton. So obviously it is F. And what you need to find? This into this, and magnitude. So this means do the determinant thing and tell me the answer. The next question is good. After these two questions, we can take a small break, and then angular momentum we are going to discuss in a great detail. And in the same way, we have 10, 11, 12, 10 or 11 important characteristics, points, examples of this angular momentum, then law of conservation of angular momentum. Two examples to observe to obtain law of conservation of angular momentum, and then this class is done. So tell me which one is the correct. Everyone got B or not? Tell me, beta. Mukeshwaram, Ashwin Karthik, or Bhuvana, Shweta, Netra, Anushika, Achya, Kanishka, Anil, they've already given the answer. So, other than him, what is your answer? B, yes, sir. What about you, this Kanishka? What is your answer? B. B. Everyone got B or not? That is very easy. F is given, R is given. Torque tau equals to R cross F. So whatever we learned in the previous class, the same thing, obviously it is a vector. So 12, 14, 16, and then magnitude 12 square, 14 square, 16 square. Do this calculation and the answer is this. Okay, try to do this. A horizontal heavy uniform bar of weight W is supported at its ends by two men. At the instant one of the men lets go of his hand of the rod, the other feels the force on his hand change to. Okay, the toppling uh, phenomena we learn. So that is related to this question. What it is states that, I give you a little bit hint to understand. There is a road, okay, and that is the road is going to be handled by two of the men. So one of the men is pulled his hand away from that particular thing. So when the initially, obviously the road is going to be handled, so that is the equilibrium, and you can say the weight of that particular road, which is mg, capital M into G, is going to be equivalence or balancing. But when one man withdraw the hand, so due to the torque, it is going to be topple, and it is going to give you some, you can say, new normal force, and you need to find this new normal force at A, or you can say at particular position, which is going to be topple up. Clear? Means simply you can see that there is initial condition. In initial condition, the two men are holding the rod, but in then final condition, when suppose this particular point is not handling the rod properly or withdraw his hand, so the A side is going to be upward, right? It is going to be topple in this way, because that particular person cannot hold the other side also, and the moment the other person, that particular person B, drops this, so it is going to in this way. So this is unequilibrium in rotational point. Clear? So what it is, one of the men lets go of his hand of the road, the other feels the force on his hand. So how much force that particular person feels on his hand to overcome this? Obviously it is not going to be, but try to. That you need to tell me. Is this clear? So two things you need to require here. The first is this, initial final case, and torque tau equals to I alpha. In one sense, you need I. So beta I here is going to be ml square by 3, and we are going to discuss this thing in the next class, why it is ml square by 3. Okay, so I is going to be ml square by 3. That is a special case of a rod. Whenever we need to find the moment of inertia of a rod from at any particular single, you can say at any particular point, which is end point. Okay, so if you need to find the end point, or you can say the moment of inertia at a particular end, at one particular end due to a rod, so that is ml square by 3. And if we need to find the moment of inertia from the particular axis which is in between, so that is ml square by 12. So you are going to use this, and you need this in this, you can say, question. So there is a hint, you going to use this, and there are two cases. So do this and tell me the answer. Okay. Meanwhile, what we can do, take a break. In between the break, you can think about this. Go for a, you can say, water, drinking water, and water so and so. At exactly after 10 minutes, or you can say around 28 to 30, we are going to start this thing again. Clear, everyone? Meanwhile, you can think about it, and you can try this question also. So there is a Break for 10 to 10 to 15 minutes. Sorry. 5 to 10 minutes. Clear, everyone? Hello, 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 hello. Okay. So anyone try this one? Are you there, beta? Hello, hello, hello. Are you there? Okay. I am going to just give me a minute. Because I class assessment test library. One minute, beta. Where is this? Yeah, it's done. Hello, hello, hello. Did you try this thing? Anyone? What is the answer of this? A, B, C, D. I'm asking to you guys. Why are you not responding, anyone? Anushika, Acha, Mukeshwaram, Anil Dev, Netra, Bhuvana, Kanishka, and then Ashwin. Anyone try this question or not? D. Okay, and I mean the Kanishka student said D. No, I don't think so. D. And if the D is answer, so how D? I want to know the reason also. Mm. tell me how D. Okay, what is the method to do this? First of all, we find the alpha. Okay, which is, you can say, angular acceleration, and then we are going to correlate with the linear acceleration. Clear? And then we are going to put into the final equation to find the force, because the net force, whenever it is going to be tilted, so it is going to be somewhere look like this. The correct answer is D, but I don't think so. You know what is the process. So what is happening here? And this is going to be the balance point when both of the person is holding, you can say, all together. But one of the person is leaving that, or you can say withdraw his or her hand. So this is going to be upward. Okay, this is force. This force is going to be apply on the hand. But altogether we have this mg component also. Okay, so this is going to give effect, and how so we are going to discuss. First of all, let the mass of the rod is m, so the weight is going to be mg. One thing, first equation, initially the equilibrium case 2f, because both applying the same force, so mg is going to be 2f plus f, which is 2f, and then this force is going to be mg by 2. When one man withdraws the hand, so the torque on the rod is torque tau equals to I alpha, and that is mg by 2. Why mg by 2? Because this force is going to be upward. Simple. And I, as I already told you, that is moment of inertia, ml square by 3 at the one end of a rod. So we are going to compare this, and we are going to find alpha. So alpha is going to be 3 by 2 GL. We know this thing on the next page, that is written over here. Linear acceleration is R into, you can say that, alpha. So here R is going to be L by 2. Why so? Because as you can see on the next page, you are going to see quite easily, R here is going to be L by 2. Okay, so the linear acceleration is going to be A, which is L by 2. This is L basically, and alpha. So that is basically 3g by 4. So now if the new normal force at A, this new normal force at A, which is F prime, is going to be mg minus this F. I mean, this is going to be downward and F also. So F, this mg minus F is going to be net force ma. So this particular force is mg minus ma, mg minus 3. Okay, this is going to be the minus sign, 3 mg by 4, because acceleration is basically 3g by 4. So the answer is mg by 4, where mg is weight. Is this clear? So in this manner you can find this thing. Yes, the correct answer is D, but that is the process to find the D. Clear everyone? Clear now? Good. Okay. So this is your angular momentum. Just give me 1 more minute, because I want to okay, I want to assign your this homework thing also. I already do. I already done for. Meanwhile, you can read this, whatever it is written over here, and you know angular momentum is simple, which is like we find the torque. So that is in the same way we can get this thing, which is angular momentum. And angular momentum, what it is? The rotational moment, we can say the momentum of an object in a rotational sense. That is almost done. I usually assign this your class assessment and homework before the class, but today I was busy a little bit. Okay, so angular momentum, the momentum of a linear body with respect to any axis of rotation, is known as the angular momentum. If P is the linear momentum of the particle and R its position vector from the point of rotation, then angular momentum L equals to R cross P, and same usually L equals to RP sine phi n, where n is the, you can say, direction of an angular momentum. Angular momentum usually also known as an axial vector, always directed perpendicular to the plane of rotation and along its axis of rotation. So I don't think so I need to explain this again and again, this axial vector and so and so. Moving ahead, as we know, momentum P, mass into velocity, that is kilogram into meter per second, and I'm multiplying R also. So that is kilogram meter square per second. Clear? That is per second is still, and joule into second also. So that is your thing. Dimension ml2 t minus 1, and that is very easy. It is similar to Planck constant also, h. Okay, angular momentum is similar to Planck constant. You're going to get to know what is a Planck constant in few time. I mean, in next class. Planck constant is h is basically joule into second, or joule into second is basically, I mean, there is a scientist, Max Planck, and that Max Planck scientist states that uncertainty principle. That uncertainty principle states that you cannot define momentum and position of any particular change in momentum and change in position of any particular wave simultaneously. If you know the momentum, certainly, so you cannot talk about the position in that much certainly, or you can say with the 100% accuracy. And if you know the position of a wave, or you can say quantum thing. What is a quantum thing? We are going to learn. Maybe you know, guys, quantum thing is the realm of small spectrum, lower than the level of atoms and so and so. Okay, so that is quantum wide. Okay, wave bias. So that is your L R cross P. Okay, in a same thing in a Cartesian coordinates, if R equals, I mean, if R is xi, yj, zk, P is going to be pxi, pyj, pzk. So then, with the help of this vector thing, or you can say determinant thing, we can find the L, which is R cross P, ijk, xyj, pxy, pyj, py, pz. So again, you can see that in Lx, because it is Lx, it is Ly, and this one is Lz. In x component, we don't have x thing, y pz, z py. In y component, we don't have y component x pz, z pz. Okay, and that is not z pz, z px. And in z component, we don't have z, x py, y px. Clear? So again, that is the proven thing. It is clear from the figure, radial component of a momentum, transverse component of a momentum, p phi equals to p sine theta. And so the magnitude of angular momentum L, which is r p sine phi and r p phi. So that is again the same thing what we already done for the torque thing. That is your diagram. The same diagram, r is still, p is in this direction and p sine phi. So either you can find the transverse component of a momentum and this particular thing which is r, position vector directly, or either you can find, or either you can multiply this p directly. Here again is nothing but r sine phi. Clear? So L is going to be r cross p maybe, or L can be r p sine phi. Wait. So from here we can do r p sine phi. So I can write p d, where d is r sine phi. Okay, and p is in this direction and d is this. So this is my r sine phi. Clear? So this is the transverse component of position vector, which is d, and this is the p phi. P phi is basically the transverse component of momentum, which is what? P sine phi. Clear, beta? This thing. So angular momentum, position vector into transverse component of angular momentum. Transverse component of angular momentum, or you can say momentum, is p phi. That is, angular is not going to be there. Transverse component of momentum, which is p sine phi. The radial component of a linear momentum has no role play in angular momentum. What is the linear momentum of a, I mean, linear component of a momentum is this. This one is the linear cos terminology, and that one is the transverse sine thing. Clear everyone? Good. Okay. So in the same sense, the same characteristic L P R sin phi, L P D S D is R sin phi from the figure. We already done this from the in the previous page. The angular momentum is linear momentum into perpendicular distance of line of action from the force, line of action or force from the axis of rotation. Maximum and minimum, same thing, because M R cross V. So MVR sin phi, P R sin phi. So L maximum is MVR, where the phi is going to be 90 degree, V is perpendicular to R, and this minimum is going to be, means angular momentum is going to be minimum or zero when this thing particular sin phi is going to be zero. That is, phi is going to be either 0 or 180 degree. So V is parallel or anti-parallel. Okay. This terminology is a particle is translatory motion. Always have an angular momentum unless it is a point on the line of action. L because L equals to MVR sin phi, and L can be greater than 1 if phi equals to 0 or 180 degree. In case of circular motion, L equals to R cross P, M cross R cross V, MVR sin phi. So because L equals to MVR, so you can put V equals to R omega. Using this V equals to R omega, we can get this relation as R perpendicular to V, and we have V equals to R omega. We can use this L equals to I omega also. How so? Again, this I equals to MR square, right? So these particular points are very, very important, because so many interrelations. Sometimes you forgot, or sometimes you don't know what particular relation is going to be used in the given thing. And very simple thing, we know L equals to MVR, we can put V equals to R omega, so we have MR square omega, and we can put MR square, which is I, moment of inertia. So we have this important relation also. This relation most of the students forget and don't use. Why so? Till this one simple thing, MVR, MV, momentum, R is this, when the momentum is perpendicular to R. Obviously we can reach up to this, but we cannot get this thing in our head like MR square can be replaced into the I, which is moment of inertia, right? So most of the time the question comes for this relation in vector form in any particular numerical, like find the, or you can say the moment of inertia is given, angular momentum is given, and they ask the angular velocity. So we do a lots of things, and then anyhow we can get a relation, but doing you can say 2-3 steps, but that is not required here because we have direct relation. Okay, and from this thing even you can see that as we have omega, so dl by dt is I d omega by dt, and we know I alpha is tau. So that is again tau is dl by dt. We can prove in another sense. I given the proof in the previous pages using the R cross P, making R constant, right? But we can use this relation as well. The rate of change of angular momentum is equal to the net torque acting on the particle. That is rotational analog of Newton's second law. So sometimes the proof of this in the, you can say finally, or you can say in your exams they can ask, or simply using the Newton's second law in a rotational aspect, prove that torque tau equals to dl by dt. Okay, and related to this, a simple numerical question. Only and only if the paper is subjective. Because if paper is, if the paper is not subjective, so the proof, derivation, and so, no one going to ask. Then you stick to this small relation, the small changes in between the formulas, and you need to find the one of the numerical, or you can say one single value. Okay, if a large torque acts on a particle for a small time, then the angular impulse or torque is given by J. J equals to T into d tau, T average which is torque, and T1 to T2. So that is change as we have impulse, right? What is impulse? Large amount of force, IMPU, like force for a small instead of time. Change in momentum, that is force into del T. In the same sense, we have impulse for you can say angular aspect, or you can say rotational thing. So that is angular impulse. That is J, torque average into del T, that is change in angular momentum. So angular impulse can also be defined as a change in angular momentum. Like we have the normal impulse change into the linear momentum. Clear? The another thing, the angular momentum of a system of particle is equal to the vector sum, and that is L equals to L1, L2, L3, and so and so. So in the same way we can add it up. This is the important thing, and we are going to use this thing again into the chapter of atoms. Okay, what it is, simply I can tell you, whenever the discovery of atom is done by in the three process. Okay, J.J. Thomson, Rutherford, and then Bohr. J.J. Thomson gives you the plum pudding model of atom. What is plum pudding? Initially, the J.J. Thomson, the scientist name I'm talking right now, J.J. Thomson thought or have an idea in his mind like the atom is like a watermelon, and that J.J. Thomson or you can say plum pudding also known as watermelon something. Okay, in which the red part is treated as a positive charge in an atom, and the black seed is treated as an electron. But obviously that is not going to be when the experimental thing is going to be done, so that is going to be free. So the another experiment is done, the Rutherford gold plate experiment. That is famous experiment in which very thin gold plate he established, and he bombarded with the electrons. Electrons also with the help of, you can say, a laser. So the when the light is going to be bombarded, so photons, or you can say charged particle basically bombard. So in that sense, when this particular gold plate is very thin, so he assumed that is a single atom. So most of the charge is going to be displaced, you can say, with a very small angle, and only 1 out of 6,000 to 5,000 particle is going to be coming back. So what he suggests, like most of the space in an atom is vacant, and you can say there is a something in between which is treated as a positive charge or positive part, because the positive charge particle repel coming back from that particular thing. Okay, and that is also known as alpha particle experiment. Alpha particle is heavy charge particle, positively charged particle, 2He4. So then what it is, so this is your Rutherford. Okay, in this Rutherford experiment, what Rutherford suggested, like there is a atom in this circular sense, obviously, and this particular circular sense we have something in between, that is nucleus, and that is quite good, and this is positive and neutral charge, and electrons are revolving. But one thing he did wrong, he make an analogy with this atom with the solar system. Okay, with the solar system, like in a solar system, the each particular planet is revolving in an elliptical orbit through you can say in the taking as a center as a foci, taking as a center as a sun. So but in this case, whenever any particular charge particle or any particular thing is going to be revolve in a center, so that particular thing is radiate energy, or specifically when charge particle revolving in a circular or in any particular manner, so it is radiate energy. So if this charge particles radiate energy, so after some time it is going to follow this path, and obviously these are electrons, so they are going to be converted towards the, or you can say move towards the positive, and it is the end of the story. Means within a fraction of time atom is going to be collapsed. But we are there, like we means every particular matter is there, so atom is there, so atom is not collapsing. So then angular, this okay, end of the story. Then Bohr, the another scientist, give the suggestion, like in each particular orbit they cannot revolve something like that. They have a fixed orbit, and the fixed orbit is related to this. concept. So this concept is what? L, which is the angular momentum of electron revolving in a, you can say, atom. It is going to be NH cut, where, or you can say, it is going to be revolve in fixed number of orbits or cell, which is related to NH upon 2 pi, where H is a Planck constant and N is an integer number. Okay, so these are basically known as stationary orbits. Means only in few specific or special type of orbits electrons can revolve, not in all. In this, they are going to revolve continuously, and that is why the stability of an atom is going to exist. Okay, so this is very important when we're going to learn again the atom chapter. So this gives us stability of an atom. Okay, where N is an integer, H is Planck constant, 6.63 value of this, 10 to the power minus 34 joule into second. That is the unit also. Okay, so N either H cut, or you can say it in general, basically that is written over like in this way, NH cut. But NH cut, where H cut is nothing but H upon 2 pi, Planck constant upon 2 pi. Okay, so that is the story of this simple thing. Clear? Got it? Okay. So the next thing, conservation of angular momentum. So as we know, or you can say from the second law of, or you can say Newton's second law for rotational motion, torque tau equals to dl by dt. So if there, or you can say if the net external torque on a particle or a system is 0, so then dl by dt is going to be 0. And when dl by dt is going to be 0, so simply it is states that L is constant. Means L is not changing with time. And if L is constant, which is angular momentum is constant, so L equals to L1 plus L2 plus L3, so and so, it is going to be constant. So angular momentum of a system, okay, then angular momentum of a system may be, you can say particle or a body system can be used as a particle or the whole body. It remains constant if the resultant torque acting on it is 0. Clear? Clear everyone? Means angular momentum is going to be constant, and it is very obvious what it is states that suppose there is a ball. Okay, what in general what you going to see, suppose there is a ball, and if this particular ball is not rotating, clear, it is not rotating now, so torque tau torque is going to be 0. Okay, you can first of all learn in an analogy with the force. What I am saying, if it is ball, is the net force on this particular ball is going to be 0. Means we apply a force on this direction, on in this direction, on this direction also, or on this direction also. So this F1 is going to be balanced by F2, and this F3 is balanced by F4. Clear? So it is not displaced from its initial position. Clear this thing? So the net force is 0. And when net force is 0, we know from the second law, rate of change of momentum also, force we can define in this way. So beta, when net force is 0, so time cannot be 0, because time is always moving from, you can say, initial to the final thing, right? So what it is 0 then? Here, this rate of change of, you can say this thing, change in momentum is 0, and change in momentum is 0 states that for this particular ball system, initial momentum, or you can say P1, P2, P3 and so is going to be constant. In a same sense, if it is any, you can say, arbitrary shape, or you can say rigid body. For this rigid body, torque tau is going to be in this direction, torque T2 is going to be in this direction, here it is going to be in this direction, or here it is going to be in this direction. Assume that. Okay, 1, then 2, and then 3, and then 4. So here it is also, all the torque is going to be cancel each other, and the net torque is 0. In the same sense, torque is what? Rate of change of angular momentum. So again, the rate of change, when it is defined as a rate of change of angular momentum, So from this scenario also, change in angular momentum is 0. And this change in angular momentum is 0 states that angular momentum is constant. Clear everyone? Clear na this terminology, this thing. So angular momentum of a system may be a particle or a body remains constant if this thing is going to be done as L equals to I omega. If T equals to 0, I omega equals to constant and I is inversely proportional to omega. Okay. Since angular momentum I omega remains constant, so when I decreases, angular velocity omega increases and vice versa. If I increases, omega decreases. Clear? Good. These are, I mean, this is just you need to know. That is not, you can say, any particular hard and fast and complex numerical is going to be, but that is very basic, and you need to know the next next two slides. Okay, I mean, in the next 3 slides we are going to talk about the conservation of angular momentum and its day-to-day life. So example of conservation of angular momentum, the first thing is the angular velocity of a revolution of a planet around the sun in an elliptical orbit increases when the planet come closer to the sun. Okay, and vice versa, because when planet come closer to the sun, its moment of inertia I decreases and therefore omega increases. What does it mean? As we know, the solar system is not moving in circular, it is moving in an elliptical orbit. Clear? So obviously, if it is moving in an elliptical orbit, the sun is, I mean, so sun is going to be situated somewhere, one of the nearest point. Okay, in this way, sun is going to be. So what it states that when Earth is rotating, when Earth is at far away, and we know this thing, we're going to learn this thing. Aerial velocity dA by dt, that is the second Kepler law, is 0, and that is L by 2m. Aerial velocity can be, that is aerial velocity, it is going to be constant, and aerial velocities can be represented by L by 2m, so that is going to be constant. Okay, so basically L is constant. So when L is constant, so again this we have, when L is constant, I omega is going to be constant, and you can say omega is 1 by I, or I is inversely proportional to omega. So as it is directly seen that at this particular farthest point, that is farthest point, and that is the nearest point. The farthest point we have R axis, I mean R high. So when we have R high, high means higher. So mr square I is going to be very, very higher. So omega is going to be less. Clear na? Here the moment of inertia is going to be high. Why so? Because the distance from the foci, distance from the sun is high. So omega, or you can say angular velocity, here is going to be very less. Here the R, the displacement, or you can say the this R is going to be less. So here the angular velocity is going to be very, very high. Got it? Because of this relation. In the same sense, a circus acrobat performs feat involving spinning and bringing his arms and legs closer to his body, or vice versa. On bringing the arms and legs closer to the body, his moment of inertia decreases and omega increases. The thing is in this way. Like a person carrying a heavy weight in his hands and standing on a rotatory platform can change the speed of a platform. When the person suddenly folds his arms, its moment of inertia decreases. Okay, its moment of inertia decreases, and accordance the angular speed increases. Is this clear? So these are basically the example of law of conservation of angular momentum. Nothing more than that. Got it? Clear everyone? Is this clear or not? Just type clear, write clear, ask anything. Why you are feeling like everyone are going to sleep just after the lecture? Am I bore you? I mean, what I'm saying. Sorry. Is this the lecture that much boring? Because I feel this now. Even I am feeling so dizzy or sleepy. Even I am teaching you. See, means today you become the most boring audience, or you can say boring, not audience, students, or batch I can refer. The best thing. Okay, so these are basically the day-to-day life example. At least this one, not the sun and everything. Even the sun and everything, but we cannot see. So just last slide, and then we are going to change the question. So a diver performs a somersault by jumping from a high diving board, keeping his legs and arms outstretched first, and then curling his body to make the law of conservation of momentum. So just basically conserve the angular momentum, so the torque is going to be zero. Effect of change in radius of Earth on its time period. As you can see, angular momentum L of the Earth is I omega. So constant. So L equals to 2 by 5 mr square into 2 pi by t. As we know, omega equals to 2 pi by time period, right? So torque tau equals to directly proportional to r square. So if m remains constant, as we know, the mass remains constant. So if r becomes half, then the time period will become 1/4. That is 24 by 4, which is 6 hours. Okay, means if we shrink the shape of our Earth, so what it is going to be, the Earth is going to be rotate very fast on its axis, and what it is, the day is going to be converted into 6 hours only. Got it? To make the this angular momentum constant. Because if it is not constant, so the Earth is going to be thrown it out away from the solar system. And if in any case Earth is going to be thrown it out away from the solar system, so we cannot have sun, and the life is going to be collapsed within 2 to 3 days, not more than that. Because sun is the primary source of energy, and when we don't have sun, so the photosynthesis is going to be, the plant is going to die as soon as possible, and the plant is going to die, the animal and the whole human being is going to be like a catastrophic effect. Okay. So this one is your question. Consider a body shown in the figure consisting of two identical balls, each of mass m, connected by a light rigid rod. If an impulse j equals to mv is imparted to the body at one of its ends, what would be its angular velocity? Everything is given. Tell me the answer. Okay. Initial angular momentum of the system about O, which is linear momentum into the perpendicular distance, and then final angular momentum of the system about O, that is I1 omega, I2 omega. Oh my goodness. And then you need to tell me omega. That is M, that is M. Okay. If I apply a impulse on this side, okay, if I imply a impulse on this side, which is j equals to capital M into v, so you need to tell me the angular velocity, with which it is going to be rotate. Oh my goodness. Option A is present in the class. Basically, here you need to apply the law of conservation of momentum, angular momentum, not momentum. Tell me what sorry. Tell me beta what is the correct answer? Anushika, Kanishika, Bhuvana, Netra, Ashwin, Karthik, Mukeshwaram, and Anil. They've already given the answer. So is he correct or not? I mean, tell me. The correct option is A, or you guys find B, C, or D. Someone. Everyone. Did you get it A or not? Okay, I'll tell you. See, initially the same thing, I mean momentum is going to be L by 2. Okay, what it is. See, initial angular momentum of the system point about point O. What is point O? This, yeah, this is point O. Because L by 2, L by 2. Okay. So initially that is going to be linear momentum into perpendicular distance of a linear momentum from the axis of rotation. That is mv L by 2. So this is tau. First, final angular momentum of the system about the point O when we apply a, you can say, this impulse. So that is going to rotate. So I1 omega 1, I2 omega 2. So we just going to find this final angular momentum of the system about point O, I1 omega, I2 omega, because with omega it is going to multiply, or you can say rotate, I1 into I2 into omega. I is ml square by 2, and then simply mr square. Okay. And how mr square? Because this is my r, this is my r, and that is L by 2, and that is L by 2 simply. So for this one mr square, for this one mr square. Okay. So that is again my torque. So applying the law of conservation of angular momentum, so means this going to be equal. So we are going to equate equation number 1 and 2. Then mv L by 2, 2m L square by 2 into omega. So simply omega is going to be v by 2. This 2 is going to be cancelled L by 2. And 1 L by 2 is going to be cancelled from itself directly. Okay. So this is how you can find your correct answer A. Is this clear, everyone? Everyone, I'm asking, is this clear or not? Mukeshwaran, Bhuvana, Kanishka, or Ashwin, Karthik, or you, beta, Anushika. Is this clear now? Okay. The same way you solve, or you solve in another way? Anil Dev. Okay. Okay. So the position of particle is given by this, and momentum is this. The angular momentum is perpendicular to. So tell me this one. First of all, find angular momentum and tell me in which direction it is perpendicular to. Okay, small hint. First find torque. Okay, you can get some in IJK form, and obviously then try to put, try to take a dot product with x-axis, y-axis, z-axis, with which axis it is going to give you 0 dot product. That axis is perpendicular to the angular momentum, because the dot product of two thing is 0 if they are perpendicular to each other. Means if the dot product of two vectors or physical quantities in vector form are 0, so that means they are perpendicular to each other, isn't it? So do this analogy. and tell me the answer. Tell me the correct answer, beta. That one is easy. Sir, is it x-axis? Yes, it is x-axis. See, that is quite easy, more easier than the previous one. L equals to R cross P. L is going to be 0, I, J and minus 2K. That is minus J of minus 2K. And the x-axis. What is x-axis? First of all, we check with the x-axis. I. So obviously, in any particular axis, if it is going to be 0, so that is going to be directly perpendicular to that axis. Because x, I into I, only we have 0. If I am going to multiply y, so we have minus of 1, and with the z-axis, okay, which is k, we have magnitude of minus 2, only perpendicular to the x-axis. Okay, so in this way we finish this particular lecture today. In the today's lecture, what we done: moment of force, torque in detail, angular momentum of a particle in detail, torque and angular momentum of a system of particles also, and then conservation of angular momentum. In the next page, you have this your class assessment. Okay, open this class assessment with this link. Okay, this is your class assessment test link. There are 6 questions in your class assessment test link. Open open those 6 questions, and if you find any particular question difficult and so, I mean, if you are not able to solve any question in those 6 questions, you can let me know. Okay. Meanwhile, I need to check your. I need to see because I upload and I know this is there. So the 6 questions are the easy one. First 2 are assertion region. Then third is you can say torque, or you can say angular momentum thing. You can find easily. Fourth is also easy, angular momentum conservation. Fifth is easy one. Sixth is easy one. Still, if you want to discuss anything, you can ask me out. Okay. In today's class assessment, each of the things is easy. Third question is torque, dl by dt. Torque 0, you can find L, or you can find the value of alpha. Because torque tau equals to R cross F. With that, you can find that. Most of the question in today's class assessment is, you can say, the theoretical one. Fifth question is directly P tau into omega. And then sixth question, a little bit tricky if you want to, but the sixth question is same like we done this question in class assessment. If one of the man is remove his hands, so how the torque is going to be? So the net torque is 0, normal into the you can say other man into x, and normal into the young man into L, and then you can find it. Okay, is this clear with everyone? Try it, and if you find any particular difficulty and so you can ask me. I am here. try that every particular question, and if you find difficulty in any one of them, so you can ask me. Okay, beta. Is this clear, everyone? Meanwhile, I assign your homework also. So homework is important. Okay, try that also. Try to solve homework 2. Okay, everyone. Meanwhile, if you want to find, if you want to ask anything, you can ask me. I'm here. I'm watching you guys. Are you doing or not? The test is visible to each and everyone now. Okay. To do that, try that. I'm here. You can ask me anything in the chat. Okay. Just going to drink a little bit more because you are not. Okay. And I'm watching you, everyone. So keep doing that. Hello, 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 hello. The test is done or not? And if you feel any difficulty so and so in any particular thing, so you can ask, because we have only 4 minutes. And if it is not, you want to try that by yourself, Okay. What are you doing, Nitra? Every question is done. You understand? Bhuvana, Kanishka, and Mokeshwaran and Anushika. What about you guys? Completed, completed, completed. Okay. So if it is completed, so we can end the class. And in the next class, we are going to talk about the MI, not MI phone, moment of inertia. Okay.